How are you today? Today we are going to discuss on factors affecting SN2 reactions, and we'll begin with discussing on the strength of the nucleophile. What is a nucleophile? Is that electron-rich species donated to the electrophilic carbon to form a covalent bond as the halides are displaced. So the nucleophile and the substrate, that is the alkyl halide, that is the nature of the substrate, and the type of solvent used affect the rate of reactions. The nature of the nucleophile affects the rate of SN2 reactions, and a good nucleophile is much more effective than a weak one in attacking an electrophilic carbon atom. For example, both methanol and methoxide ion have easily shared polarizable pairs of non-bonding electrons, but methoxide ion reacts with electrophiles in the SN2 reactions about 1 million times faster than methanol. It is generally true that a species with a negative charge is a stronger nucleophile than a species without a negative charge. The methoxide ion has non-bonding electrons that are easily available for bonding. At this transition state, the negative charge is shared by the oxygen of the methoxide ion and by the halide leaving group. However, with methanol, which has no negative charge, the transition state has a partial negative charge on the halide ion, but a partial positive charge on the methanol oxygen atom. As in the case of methanol and methoxide ion, a base is always a stronger nucleophile than its conjugate acid. So if you consider these two, this is the base and this is the conjugate acid of this base. So the base is always a stronger nucleophile as compared to the conjugate acid, as compared to the conjugate acid. And this conjugate acid can be formed by protonating this methoxide ion. So this is a reaction between the methoxide ion, which is a stronger nucleophile, and it's a conjugate base of methanol, which is the conjugate acid. So it donates electrons towards forming a new bond with this electrophilic carbon. And of course, this reaction, that is the SN2 mechanism, is usually concerted and it's a one-step reaction. So everything is forming at the same time and leaving at the same time. So the bond will start to form as the leaving group is also this covalent bond is starting to break so that the leaving group leaves. So in the process, there will be a transition state, which is a high energy state. But the difference between when the conjugate base, which is a stronger nucleophile, is donating electrons to the electrophilic carbon to form a new bond, and when a methanol, which is a neutral molecule and a weaker base or a conjugate acid, is being used to form a new with electrophilic carbon to form the final product, which in this case is an ether, is that when a conjugate base is used, which is a stronger nucleophile and which has got which has a negative charge is used, the oxygen in the transition state, the oxygen will still bear a partial negative charge, which will be donated towards neutralizing the partial positive charge on the electrophilic carbon. Together with the iodine atom, also has a partial negative charge, which will be shared with the electrophilic carbon towards neutralizing the partial positive charge. So this will require a lower activation energy because both the two atoms which are bonded partially to this electrophilic carbon are trying and neutralizing that partial positive charge because they are got partial negative charge. So to form the final product, so you have the ether and the leaving group. But when the conjugate acid is used, which is the weaker nucleophile, so what happens, of course, a lone pair of electrons is used to form a new bond with this electrophilic carbon. Then we have a transition state, but the activation energy in the transition state here is higher because this is more unstable as compared to when the conjugate base is used to form a new bond to the electrophilic carbon. And you can see here clearly When you have the transition state, you can see oxygen has a partial positive charge, so it's not able to stabilize the partial positive charge on this carbon atom, this electrophilic carbon. But of course, it's being stabilized by iodine atom, which is negatively charged, just as in the other case. So it's only being stabilized by iodine atom, but not by the oxygen atom. Of course, that means it is not as stable as the transition state of when the conjugate base is used. So that's why you see this one is a higher activation energy as compared to the one when the stronger nucleophile is used. So again, after that, this is the next process where this bond has completely formed, but there's still a positive charge, and therefore the base here, in this case, the iodide ion is going to abstract this proton, acidic proton, because it has a partial positive charge, leave behind 2 electrons, which will stabilize that positive charge on oxygen, and it forms the ether. Basicity and nucleophilicity are different properties. Basicity is defined by the equilibrium constant for abstracting a proton. Nucleophilicity is defined by the rate of attack on an electrophilic carbon atom. In both cases, the nucleophile or the base forms a new bond. If the new bond is to a proton, it has reacted as a base. And if the new bond is to a carbon, it has reacted as a nucleophile. Predicting which way a species will react may be difficult. Most but not all good nucleophiles are also strong bases, and vice versa. So in this particular case, when you have this electron-rich species forming a new bond with a proton, acidic proton, of course a hydrogen with a partial positive charge or complete positive charge, hydrogen positive charge, then it is acting as a base. So you can see here, this has the electron-rich species has donated the electrons to form this covalent bond to hydrogen, so it's acting as a base. But if the same electron-rich species is used to uses the 2 electrons to form a new bond to an electrophilic carbon atom, then it acts. You can see here it's in blue. So these are the source of this covalent bond, or the 2 electrons of this covalent bond are the electron-rich species here. And in this case, since it's using them to form a new bond to carbon, it's going to be known as a nucleophile. So I will stop there. Next time we will discuss on some common nucleophiles listed in increasing order of nucleophilicity in hydroxylic solvents such as water and alcohols. Thank you.